in the study and application of gases. Gases as a form of matter is quite different than solids and liquids. Each substance that we work with has a particular rate of contraction or expansion due to temperature change. Gases respond much more than that. Their coefficient of expansion is much greater. It has been shown by numerous experiments that all gases have the very same rate of contraction due to change in temperature. Approximately 1 over 273, or 1/273rd the volume of a given volume of air or gas, any gas, will change for each degree change per degree Celsius. If this rate of contraction would take place all the way down to 273 degrees below zero on the Celsius scale, theoretically the volume would reduce to zero. Now, common sense tells us that nothing can have a zero volume, that is, if it's made out of matter. However, the theoretical value of that has been the basis for suggesting in the theory that the absolute coldest of anything can be 273 degrees below zero. This is quite often called the Kelvin scale because a man with this name is the one that devised it. It's pretty well established that the temperature of any substance is due to the movement or the vibration of the molecules that take place in it. At that temperature, it is believed that all movement stops. As we heat any substance, it speeds up the movement of the molecules. Now, in solids, this takes the form simply of a vibration. As that temperature becomes high enough in various materials, the molecules break loose from each other and they roam around in what we call the liquid state. Further heating, as it speeds them up more, and as they escape from the liquid, we then have what we call a gaseous material. At that point, the molecules are far enough apart that the gas is usually invisible. What we're going to try to demonstrate now here, in chemistry, we have a quantity called the molar volume of any gas. To identify the quantity of a gas, quite often we use the pressure and volume values established at some standard. For pressure, we use the atmospheric pressure that's been averaged out at sea level, and this can be measured in inches of mercury, or in a metric system it would be centimeters. Turns out that 30 inches of mercury, using a mercury as a gauge for this, or 76 centimeters, which would be 760 millimeters, is what we call standard pressure. And so in describing any gas, the quantity of it, we have to identify it in terms of its temperature and also the pressure. Now, the temperature standard has been adopted to be at the freezing point of water, which would be 0 degrees Celsius. On the Kelvin scale, this would be 273 degrees. What we're wanting to do here is to show the theoretical value of that molecular volume as 22.4 liters is approximately the volume we see in this glass jug. The glass jug is 5 gallons. It wouldn't quite be it, but it's here to help us visualize these relationships. It turns out now that if we'll say we would take that molar volume, 22.4 liters, and could reduce it down to absolute zero if the gas followed that rate of contraction all the way down to what we would call 1 degree. The theory is that it would then occupy a volume equal to 0.08 liters. Now that's the volume of a copper container that I have designed that represents that volume. Right by the side of it, we have a glass vial of approximately that volume. It turns out that when we do this experiment, we will not be going to absolute zero, but by using a tank of liquid nitrogen, which is obtained by distilling liquid air. Ordinary air is a mixture of nitrogen and oxygen, and when it's reduced to 195 degrees Celsius, at that point air will change into a liquid. Now air contains, in addition to nitrogen, the substance oxygen. The liquid air then, if allowed to warm up, will boil at 195 below zero. And it is separated from the oxygen simply by boiling it off first, capturing it and reprocessing it into liquid nitrogen. The oxygen will boil off at about 180 below zero. Once the nitrogen is removed, then the oxygen is extracted, compressed into cylinders to be used in welding and processes like that. What's contained in our tank here now is liquid nitrogen, commonly known as air gas. And it's the result of mechanically separating these two elements. What we will do in our experiment now, we will lower this. We'll fill this bucket full of water. The glass jug is vented to the bucket through a two-hole stopper, one of which goes to the bucket, the other will go to this copper tube. As we lower the copper tube into the liquid nitrogen then, as it contracts that gas, it will create low pressure in the glass jug, and it will shrink that gas enough so that practically all of the water in the bucket will fill up the glass jug. Now it won't go all the way because the temperature will not go clear on down near absolute zero. The temperature of the liquid nitrogen on the Kelvin scale would be about 78 degrees. Now later in this film, you will see where we have done this experiment, and I made some comments that were inaccurate. I made a comment that the temperature of the liquid nitrogen on the Kelvin scale, I said, was 58. That's wrong. So I'm correcting that now, so you'll be prepared for that when we get to it. It's very remarkable now that this cylinder on the left is the one that we will use to represent what we call the gas constant. In other words, the letter R represents that theoretical volume that you would have at 1 degree Kelvin. That's 0.08 liters, or that would be 80 milliliters. Now in the demonstration you'll see I have another copper tube that I had fashioned. We used it in this experiment, and it is only about 3/100 of a liter, and we'll find that it will fill the jug about 1/3 full. That display will come first, but the important one is the one that you see using the bigger tube. Now as the experiment, or as the display takes place, this will follow our introduction here, which I'm making to make some of the corrections that we will be referring to. And I want to emphasize again that in the first process here, we'll be using the small tube. Now, it will not come any ways near filling the jar full. So bear with it till we get to the one where we use this one, this tube here. This is sort of referred to as the gas constant. In other words, we see a formula here in which the pressure in atmospheres times the volume that we will end up with will be equal to the number of moles. The number of moles would be the number of quantities of 22.4 multiplied by this R. This then multiplied by the absolute temperature, or Kelvin. By this formula, we can calculate what this volume would be under the particular conditions of pressure and absolute temperature. But we will not continue with a discussion of that because it is really reserved for a little bit more advanced calculations in gases. Our purpose here mainly is to dramatize how much this gas will shrink due to reduction in pressure. What we have found is that with the use of this tube here, it would approximately draw that jug about 2/3 full, because the shrinkage action is going to stop at 195 below zero, which is, as I said, 78 degrees above the absolute value. So we'll stand by now and get ready for all of the displays. Now, in addition to this, we've done a number of demonstrations showing the effect of liquid nitrogen on supercooling an aluminum ring. We do another one where we freeze some of the things with low freezing points, such as mercury, even gasoline and methanol. These will all be demonstrated in the series of films that you see. In addition, we will show the behavior of gases in a rarefied atmosphere, the electrical effects of it. So we'll stand by now till we get ready to put these demonstrations on a major tape. What we want to demonstrate at this point is the behavior of gases. The purpose of this is to show how much a gas will contract when exposed to very low temperatures. What we see here is an arrangement whereby 1 mole of gas at standard temperature and pressure is 22.4 liters, very close to 5 gallons. This will be displayed by a 5-gallon jug. In the container we have liquid nitrogen, whose temperature is 195 degrees below zero Celsius. The purpose is to show and dramatize the great amount that a gas will contract when exposed to those very low temperatures. In a previous scene, we described, or will have described, the rate at which gases contract, which is 1/273 of the volume. Extrapolating that amount from zero down, it would suggest that any gas would reduce to a volume of zero. Now, of course, common sense tells us that nothing could go to a zero volume. turns out that what gases do at certain temperatures, each gas has its own specific pressure and temperature at which it will liquefy. Now, ordinary air can be compressed and cooled to that point where it will change into a liquid. What we have stored in this container is a special kind of thermos container that will contain liquid air. However, liquid air is a mixture of oxygen and nitrogen, and so that liquid air has been allowed to boil, in which the oxygen will boil off. So what we see in the container is about 5 gallons of liquid nitrogen, sometimes referred to as air gas, used in many experiments, particularly in cattle and hog breeding, to freeze sperms. Even human sperms have been frozen and preserved for artificial insemination. The purpose here is to show the theoretical value of that 1 mole of gas, what it would be if it were to contract according to that rate to the full 273 degrees. So we have what we call the Kelvin scale, in which that point is called absolute zero, developed by a person by the name of Kelvin. It's called the Kelvin scale. Theoretically, this 1 mole of gas, which is 22.4 liters, if it were to follow that through, would contract down to this volume right here, which is called R. It's called a gas constant, and is approximately 0.08 liters. It turns out, however, that it will reach that point even before it goes to absolute zero. Now we're going to try to show now how much that will occur. We will do so by raising the lid here and immersing this down into the liquid nitrogen that's inside this container. We'll stand by now till we can get ready to carry out that particular part of the demonstration. Just another view here to show the values on those containers and the amount that they represent. Now, a 5-gallon jug would not quite be 22.4 liters, but this will help to emphasize that relationship. Same thing with the boiling point of liquid nitrogen would be 1 minus 195. If we subtract that from 273, it would be about 53 degrees Kelvin on the Kelvin scale. We'll now try to get things established to start our experiment to see the action that will take place as that gas in that glass jar is evacuated by means of shrinking it due to the cooling effect. Now there we can see the action already starting. You can see water being drawn into that jar. And we just let this go till we see how much it will extract from the bucket of water. Now there we can see the water is being drawn from this bucket. Now we'll stand by on the camera at intervals because it'll take quite a while for that complete action to take place. Now I've repositioned the camera so we can get a little bit better close-up view of the action. This is another view now, taking a little bit later. We can see the volume of the water is at this point well beyond even the volume of that copper tube that's down in the liquid nitrogen. We'll continue there at periodic times to stand by until the action is as far as it will go. As we can see, the depth of the water is continually increasing. If we look within the bucket, we can see that the water level there is measurably decreased. And we'll continue to stand by and continue to film at intervals. Now we will see here that the volume is enormously increased and water is still coming out. And so we'll stand by on the camera again here to rolling.
Now that seems like it's pulling up a lot of water there for that little thing you put in there. How's that working?
What's that?
That little tube, you just put that little tube in this 195 degree below zero, and just a tiny little tube.
You might need to talk a little louder.
And you're moving
Your question?
all that water with just the volume of cooling that little bitty tube.
All right, you just asked the question that we started out with, that small tube. Gases contract considerable amount compared to solids and liquids. What you're looking at there is a very cold temperature, and that little tube will get cold. It'll shrink the